All right, so far what we've studied linear functions, of the form f of x equals mx plus b, m is the slope, b is the y-intercept. We've studied exponential functions, a times b to the x, and we've studied quadratic functions now as well, of the form ax squared plus bx plus c if we have it in standard form. And what they want us to be able to do in this section is recognize from a set of data whether the function is linear, exponential, or quadratic. And here's how we do that. To determine the function type, we take what we call the first differences. And the differences between consecutive y values are the first differences. So the difference between -1 and 1 is 2. The difference between 1 and 3 is 2. The difference between 3 and 5 is 2. And the difference between 5 and 7 is 2. So when the first difference, okay, take the difference between consecutive y values, when the first difference are the same, are constant, then we say this is a linear function. This is best modeled by a linear function. So if we were to put this data into our calculator and ask for the regression, we would ask for the linear regression because we recognize that it's a linear function. Okay. So then we move on to another example, and here the first difference is, between 3 and 9 is 6, between 9 and 19 is 10, between 19 and 33 is 14. So obviously the first differences are not the same, therefore this is not linear. Okay. The second difference is the differences between the first difference. So the difference between 6 and 10 is 4. The difference between 10 and 14 is 4. And the difference between 4 and 18 is 4. Therefore, when the second difference is constant, when the second difference is all the same, then we say this would be best modeled, what I was really going to spell there, by a quadratic function. So if we were to put this in a graphing calculator and tell it to find the regression, we would ask it to find the quadratic regression because that's what makes the most sense. Okay. Now we get to this, and what we have here is the set of data. We found the first difference. The difference here is 1, then 2, then 4, then 8. So it's not linear. And then the second difference, the difference here is 1, the difference here is 2, the difference here is 4. So not quadratic. Okay. And then we eliminate these, okay? And we're not going to use them for my third thing. For my third thing, I'm going to find the ratio of the y values. So I'm going to take 2 divided by 1, I get 2. I'm going to take 4 divided by 2, I get 2. I take 8 divided by 4, I get 2. I take 16 divided by 8, and I get 2. And some of you might be thinking, well, the ratio, the common ratio, if there's a common ratio, then that's a geometric series or geometric sequence. And you're correct. Geometric sequences are exponential. And so when we have that common ratio, we know then that this data over here is exponential, that this is a exponential function. And we even have an exponential function best models the data when the ratios of consecutive y values are the same. Okay. So How are we going to be doing this on the homework? Well, it will give us a table of values, and they'll tell us, what is it, linear, is it quadratic, is it exponential? What best models that. So we find the first difference. The difference between -2 and -5 is -3, and then -9, -15, and then -21. So not linear. And then we take the second difference. The difference here is -6. The difference here is -6. There we go. So the best model, or if I were to ask for the regression, it would be quadratic. It's a quadratic function. And, and sometimes this might be off when we're looking at like a very real set of data. This might be off by a decimal point. Okay, that doesn't mean that it's not quadratic. If this fails, if the ratio of the y value fails, then we look back and say, well, this was very, very close. So we're going to say it's a quadratic function. Another example, the difference here is 8, and then what is 36 minus 12? 24. 108 minus 36 is 72. 324. Doing this without a calculator, so hopefully those are correct. So obviously not linear. Okay. Then we go to the second difference, and that difference is 16, 48, and 144. Okay, so not quadratic. And then 12 divided by 4 is 3, 3, 3, 3. So the best regression is this is an exponential function. And we could use our idea about a geometric sequence. Series comes much later in path. But we could write the first term is 36 times 3 to the n minus 1 we used, I think. That would be like, I don't know, f of x or f of t or something. I think we used a of x actually. So I think this gives an example of what I was talking about earlier. And we go for that first difference. We get the first one's 21 cents. 21 cents. The second one is 31 cents. The next one is 42 cents. And the last one is 53 cents. So not linear, right? This differs by 10 cents, this by 11 cents, and this by 11 cents. And so this is what I was talking about where, that difference is minuscule comparatively. So, so we say that this is quadratic, best modeled by a quadratic function. And I'm not going to do those other two questions. So to summarize, linear functions. F of x equals mx plus b. Graph of a linear function is a line where the slope is m and the y-intercept is b. Exponential functions are functions we graphed that looked like this, where the x-axis is actually an asymptote. It's going to get closer and closer and closer, but it's never going to touch. And then quadratic functions in standard form. Graph of a quadratic function is a parabola. It can open up. It can open down. It can have y-intercepts. It has a it can have x-intercepts. It does have a y-intercept, and has a vertex, which could be a maximum or a minimum. And we can also express that in graphing form. And then absolute value is the v. And we can translate that just like we can translate the quadratic functions. So that's just a summarization of what we've learned about graphing so far and what we should be able to recognize. We should be able to look at a function and say, oh, that's a quadratic function. It's going to be a parabola. It's going to have a vertex. It's going to have a y-intercept. It might have some x-intercepts, et cetera, and so on. Or that's an exponential function, and it has a common ratio, and it grows exponentially, and we use it to model, interest problems and such. So that's that for that, and that is the end of the chapter, or end of the topic, end of topic 8.